Hey guys, welcome back to Spark AR Scripting. My name is Zohil, and in today's episode, we are going to be covering shaders, what they are, how they work, and what you can do with them inside of Spark. Alright, so let's get started. So I've basically set up this empty project again, which just has a simple screen effect setup similar to the first episode. So we have a canvas, a rectangle, and a material with a flat shader on it. And what I'm going to do is create a script, and we'll use it to control what our material displays. If you're not familiar with this setup, check out the first episode where I walk through all of this in more detail. Okay, so once it's loaded, so this time I'm just going to go and delete all of this, and we'll start from scratch. So let's just go and add our main function again, and we'll just add our simple setup where we display the camera texture on the rectangle and then go from there. So what we're going to need to do is load in a few modules. So we need the shaders module, so let's require shaders. Then we need the material module, which is require materials. Then we're going to need the textures module, just require textures. And we'll most likely be doing some reactive stuff, so let's add in the reactive module. Okay, and then we can just load in our default material equals m.get, and it's called material 0. And we got the camera texture, t.get, camera texture 0. Okay, and so as mentioned before, this is now deprecated, and we'll need to use promises going forward, which is something I'll cover in one of the next few episodes, so stay tuned for that. But for now, it's okay to just do it like this. So we'll go ahead and load in our UVs. It's const UV equal s dot vertex attribute, and then basically you have to give it a config with a variable name and one of the attributes here. And we're going to use vertex attribute dot text chords, so it's s dot vertex attribute dot text chords. And okay, and just to note, so a few people ran into this in the first episode. When you just type in s.vertex attribute and you hit tab, the autocomplete is going to set this to a lowercase v, and that's actually the name of the function. Whereas this enum actually needs to be an uppercase v. So if you hover over it, you can see over here, it's basically vertex attribute with a capital V. So you basically just take it from here and paste it. So, and for some reason it'll give you this red line over here, and that's a bug in the autocomplete. For some reason it thinks there needs to be a lowercase v here, but it's actually an uppercase V. So just be aware of that if you ran into this. Okay, and then what we want to do is just sample the color, which is s.texture sampler, and you just pass in the camera text.signal and the UVs. So now we have the color, and we just output it to the material, and for that we can use the texture slot from here, which is basically the diffuse texture slot. So then we can just do default material dot set texture slot, and we give it the texture slot and the color. Okay, so now if we go back to Spark, let's just see. Shaders does not exist because basically we were calling it S, so just rename it, and there you go. So this is basically what we had in the first episode, with just sampling the camera texture and putting it on the rectangle on the screen. So what I'll do now is explain this in a bit more detail from a shaders perspective. Alright, so what exactly are shaders? Basically, on any modern processor, like your desktop computer or one of the new phones, like an iPhone or any smartphone, basically, you're going to have two main processors. There's the CPU and the GPU. So the CPU is the central processing unit, and the GPU is the graphics processing unit, and they're also known as graphics cards in the desktop world. So the difference is CPU is mainly used for general purpose tasks, and it's good at handling all sorts of problems and doing multiple things at the same time. Whereas the GPU is optimized for graphics processing tasks. stuff like image processing and geometry processing, and it's good at doing one thing at a time, but it can do it in parallel on multiple items. So basically, a shader is just a program which runs on the GPU. So when you create a regular computer program, it generally runs on the CPU. And when you create a 3D application which does image processing or geometry processing, all those graphics operations are usually offloaded to the GPU, and they run on the shader units in the hardware. So again, shader is just basically a program for the GPU. And yeah, so like I mentioned, GPUs are massively parallel, basically. So there's thousands of cores on these things, and they're the shader units. So when you do something like an image processing kernel, like what we have here, it's basically going to sample camera texture for every pixel on the screen. And all this happens in parallel on the shader units. So instead of doing it one pixel at a time, it's doing multiple pixels at a time. So basically, it runs the same code on a bunch of different items at the same time, which is what makes GPUs so fast. So the implication of that is GPU code tends to be very linear. Like, you can't have a lot of branches and stuff. You can't, but it slows the whole thing down. Like, it's much more optimized for doing the same type of stuff on multiple different items. Whereas as a CPU, you can have all kinds of branches and different types of user input and all kinds of stuff going on, and it handles that pretty well. So that's mainly the difference between the two. So as far as shader programs, they're mainly written in a language known as GLSL, which is the most popular. There's a few of them, but there's an OpenGL graphics library which has GLSL shaders, and Spark under the hood. When you do something in the shader module, it converts all your shader signals into GLSL code. So if you hover over this, you see camera text.signal. It's converting the texture into a shader signal. So basically that just means it's passing the texture into the shader, and then all operations after that are going to be inside the shader code. And if you look here also at the top of the shaders module, there's a note, signals returned from this module will not work in any other context. That's basically, it's the same reason, because the rest of your Spark reactive code is going to run on the CPU, whereas anything in the shaders module, it's going to run on this different processor, which is the GPU. And once you're in the shaders module, so once we do Vertex attribute, all this is going to get compiled into shader code. And if you do anything before that, that's going to get compiled into CPU code. So Spark is basically a one-way street. Once you send your data over to the GPU, the only way to actually see it is by either modifying the vertices or the pixels in the screen. So you can see the output, but there's no way to get it back to the CPU. Outside of Spark, there are ways to get data going back and forth between the CPU and GPU, especially in unified memory architectures, because it's the same memory address space. So you can basically just write to memory and the CPU can read from that. It's just a matter of synchronizing the data. But in Spark, that's not supported. So for now, it's just once you're in shader land, it's just going to stay there. Okay, so as far as the types of shaders go, there's actually many different types of shaders, but Spark mainly supports two of them, which is Vertex shader and pixel shader. This is also known as a fragment shader. And so the Vertex shader is responsible for doing operations on vertices and transforming them to pixel space, versus the pixel shader is responsible for generating color outputs. So the way this works is basically, let's just take a look at our quad over here. So if we zoom into this, we basically see it's got a bunch of points on the corners, and those are the vertices of this quad. So let's just assume it had three vertex points here, so it'll be two triangles, one like this, one like this. Then basically, so what's going to happen is Spark's going to send that over to the graphics card. Then it's going to take all the vertices, run the vertex shader, and if you don't have them, it'll basically just run a default vertex shader, which transforms them to pixel space. So it's going to take all the vertices of your triangle, transform them to pixel space, then it'll cull them and clip them, and run it through the rasterizer, which will convert those points into basically fragments. Then those fragments go through a depth test if you have it enabled, and then it's sent to the pixel shader units, and then the pixel shader calculates the color, and that's sent out to the final texture, and that's what you see on the screen. So basically the hardware does most of this behind the scenes. So you basically just have to worry about the vertex shader or the pixel shader code. So the interesting thing to note is, how do you know whether this code is going to run on the pixel shader or the vertex shader? So generally, if it's doing any type of vertex processing, it's going to run it on the vertex shader, even if it's just calculating vertex-based values. And if it's doing anything like a texture operation or an image operation, it's going to run on a pixel shader. So as a rule, Spark will basically, when you set up your code, it's going to try and move everything as far back as possible. So we have 3 stages involved. There's the CPU, there's the vertex shader, and the fragment shader. And the earlier you go in the chain, the less computation you have to do. So if you think about it, basically the CPU is just running your code once per frame. Then the vertex shader is running your code once per vertex. And in the case of our quad, there was like 6 vertices. And then the fragment shader is running your code once per pixel. So if the resolution is like 1080, so 1920 times 1080, that's like 2 million pixels. So the earlier you run your code, the faster it's going to be, because it's doing a lot less work. So once on the CPU, 6 times on the vertex shader, and then 2 million times on the pixel shader. So Spark is set up to try and move as much code as can earlier in the chain. So if it can run it on the CPU, it'll run it on the CPU. If it can run it on the vertex shader, it'll run it there. Otherwise, it'll do it on the pixel shader. So let's just walk through this and see where it's trying to run the code. So over here, it's basically doing a vertex attribute, which is getting us the UVs of the quad. So this is going to happen on the vertex shader. Then over here, we're computing the color. That's, of course, going to happen on the fragment shader, because it's running per pixel, because the color is computed per pixel. And then finally, outputting it is also going to be in the fragment shader. So this is basically just writing it to the texture. So the other thing to note is, how do the UVs come from the vertex shader all the way over to the pixel shader? Because as we discussed, there's only 6 vertices and there's 2 million pixels. So how does each of the pixels get access to a UV value? And that's basically done through something known as the interpolators. These are basically units on the hardware which take the outputs from your vertex shader, interpolate them across the triangle, and send them to the pixel shader. So like I said, your triangles are going to get rasterized into fragments, and those fragments have a bunch of inputs, which are the interpolated values which come out of your vertex shader, and that's sent to your pixel shader, and it can use them to do a bunch of per pixel operations. So to generate these interpolated values, it uses something known as barycentric coordinates of the triangle. You can look this up on Wikipedia if you wanted more detailed explanation. And the type of interpolation is known as perspective correct interpolation, which basically just means that regardless of the camera angle or perspective you're using, it'll always be correct. So the values the pixel shader gets are interpolated across the triangle. So basically it takes these 6 values and gives you a per pixel interpolated value, which you can use in your fragment shader. So in this case, we're just using the UVs. So it's going to take the UVs from the vertex shader and interpolate them into the UVs of the fragment shader. So that's basically what's happening behind the scenes. So we calculate the UVs in the vertex shader, which is just going to pull them from memory out of the mesh, and then it's going to interpolate them across the triangle, send them to the fragment shader. Okay, so all this is fragment stage shader basically. I'll try and show a visual example of this. And that also brings up this other point of, as I had mentioned, there's no way to get data back from the shaders back into the CPU land. So if you want to debug your shaders, the best way to do that is just visualize the intermediate calculations onto the screen. So basically just output whatever you want as a color. So in this case, I'll just show you what the UVs actually look like once they're interpolated. So what I'll do is basically just map the UVs to the colors. So we'll create this UV color variable, and UVs are 2-channel. There's an X and a Y. So we have to convert it to a 4-channel because we want an RGB. So we do r.pack4, we give it uv.x, and then uv.y, and 0, and then 1. And now you can just create a final color equals UV color, and then just send that to the output. Okay, so now if you go back to Spark, so we basically see this gradient, and that's representative of the UV values interpolated into pixel space. So over here we have 0, 0, which is black. Then over here we have 1, 0, which is red. Over here we have 0, 1, which is green. And over here we have 1, 1, which is yellow. And in between, you're basically seeing a mix of those colors. So it's interpolating between those colors. And so every pixel is going to see a different UV value in the pixel shader. And you can use that to do all kinds of stuff, like sample the texture or do operations based on this. And you can also just do all kinds of effects using this information. Okay, so just to illustrate this in a bit more detail, I'll show you an example of splitting the screen into two. So we'll split the screen across the middle, and on the left side we'll do one effect, and on the right side we'll do another. So if you go back to Spark, as I'd mentioned, UVs go from 0 to 1 over here, and you can see that. So the middle is basically going to be 0.5. So 0.5 in the X and 0.5 in the Y is the center point, and 0.5 in the X is basically splitting it into half. But as I mentioned, you can't do branches in shaders, and in general in reactive code you can't do branches anyway. But in shaders it's even worse because the shader units are much more optimized to run the same code for every pixel. So basically when you want to branch, you can use what's known as a step function. And in the first episode we had covered the sine function. I'll just show you the graph for that. So yeah, if you go to Wikipedia, this is basically a sine wave, which basically is just mapping points along a circle as the values get bigger and bigger, and it just keeps going in the circle, and you see this wave type of output. Similarly to that, a step function is basically this, where if the value is less than the step value, it's going to give you one number, and if it's greater, it's going to give you another. So in this case, anything less than 0 is going to give you 0, anything greater than 0 is going to give you 1. If you look at the reactive module documentation and you search for step, then basically you can see it says return 0 if X is less than the edge and 1 is returned otherwise. So we can use this information to split our scene based on the UVs. So what I'll do is just create this variable known as split, and that's going to do r.step. And what we can do is pass in the X value of the UVs, and for the edge we give it 0.5. So what it's going to do is, if the X coordinate of the UVs is less than 0.5, it's going to return 0, else it's going to return 1. So basically it's X less than 0.5, return 0, else return 1. That's basically what it's doing. Now what we can do is just, instead of just outputting the UVs, we can just output this just to see what it looks like. So again, like I said, if you ever want to debug shader code, just output it to the screen. That's the best way to see what's going on, is by visualizing the results. So we do splits, we replicate the split value across the channels, and then if we go here, so you basically see this gradient over here, and that's not split down the middle. What it's doing is, as I'd mentioned, Spark is going to try, if you go back here, it's going to try and run this step function as early as it can. So we're taking the UV coordinates in the vertex shader, and then we're doing step. So Spark is going to try and optimize that and run the step function on the vertex shader, and then send the interpolated values to the pixel shader. So in that case, we end up with this gradient over here. But what we wanted is a hard line between the middle. So in effect, we basically wanted to run the step function per pixel, so that every pixel does this test. And if it's less than half, it gives us black, otherwise it gives us white. To do that, what we can do is basically use this function known as fragment stage. So what that does is places the subsequent computation to the fragment stage. So what we can do is pass the UVs to the fragment stage, and that's going to give us the fragment UVs. So instead of basically running our calculations in the vertex shader, it's going to move whatever calculations use this value to the fragment stage. So now if we run the split function on the fragment UVs and go back, we basically see this hard line because it's now running this test per pixel. So that's basically how you decide which stage to run your operations on, whether it's on the vertex shader or the fragment shader. Okay, so now basically this is also moved to the fragment stage. Okay, so hopefully that makes sense, and that should give you a better idea of what the different shader stages are and how you can figure out where the code's going to run and move it based on where you actually want it to run. Okay, so just one more thing. So over here, we basically use the step function. Similarly to that, we have the smoothstep function. And what that does is, instead of a single edge, you can give it two values, an edge 0 and an edge 1. And basically, if your value is less than the first edge, it'll return 0. If your value is greater than the second edge, it'll return 1. But if it's in between, it's going to give you an interpolated value. And it uses Hermite interpolation for that, which you can look up on Wikipedia. So if we don't want a hard line, but we want some kind of soft edges, then we can use the smoothstep function for that. And this is basically pretty similar. So what we can do is just do smooth split with r.smoothstep, and you just again give it the fragment UVs, and then 0.3 and 0.6. So now if it's less than 0.3, it's going to return 0. If it's greater than 0.6, it's going to return 1. And if it's in the middle of that, it's going to interpolate the values and give us like a gradient. So for that, let's call this SS, and we can put this in here. Okay, and now if you go back to Spark, there, so you see like a soft edge in the middle. So it's not such a hard line, and basically we get this interpolated value. And since we have that, I thought I'd just show you, basically, if we set this to 0, and if we set this to 1, that's basically the same as having this calculation run on the Vertex shader and get the interpolated value. So if we save this and go back, we see the same thing as what we saw when the Vertex shader was doing the step function and interpolating the values across. So, but instead we have more control, so let's just set it back. Use the gradient instead. So now that we have this black and white value, we can actually use this as a mask to control what effects show up on the screen. So we can use this to create two different effects and use the mask to control which effect shows where. So we can have one effect on the left side of the screen and one effect on the right side of the screen. So I'll just show you that. So let's just do a simple sine animation like we had in the first episode. So I'll just do once time equals require time. So we can basically just do seconds equals time.ms, and we multiply this by 0.01, which is 1 over 1,000. And then we can do, just create a curve using the seconds. And what we want it to do is have it go from 0 to 1. So now we can create two colors. Let's say left color equals r.pack4. Let's just create it red, so it's curved. So it's using the curve in the red channel. And then the right color can do it for the blue channel. Okay, so now we have two colors, and now what we can do is use the mix function. So if you go to the documentation, there's this mix over here, and that gives you a value that is interpolation of two signals. So this is also known as lerp, or linear interpolate, and the way it works is basically you have three values. You have A, B, and T is the interpolation value, which is between 0 and 1. So what this does is it's going to do A times 1 minus T plus B times T. So let's just run through some simple examples. Let's say we pass in 0. Then we get A times 1 plus B times 0. And that's going to equal basically just A, because B times 0 is going to be 0, and A times 1 is A. And now if we pass in 1, it's going to do A times 0 plus B times 1, and that's going to give us B. And if we pass in 0.5, it's going to do A times 0.5 plus B times 0.5. So it's going to be half of A and half of B. So basically, it's blending between two values based on this input you give it. So 0 is going to give you the first value, which is A. 1 is going to give you the second value, which is B. And anything else is going to give you a blended or an interpolated value, similar to all this interpolation stuff we've been seeing so far. So what we can do is use our mask as the blending value to blend between the left and the right color. So what we can do is blend color equals r.mix, and then we give it the left color, the right color, and for the mask we just give it basically our smooth step function. And then we can, instead of the final color, instead of the UV color, we can just output the blend color. Now if you go back to Spark, you basically see this blend between red and blue. And instead of that, what we can do is actually, let's just take the color here and move it here, and then what we can do is add this to the curve to make it look a bit more interesting. And now if you go back to Spark, you basically see this blended value between red and blue. And we can also multiply if you prefer that. So this will make it all darker, because adding colors is additive, so it brightens everything, but when you multiply it darkens everything. So now we have this dark tint to it. And we can even just mix it up, so bright on one side and dark on the other. And what we can do is actually even just animate the UVs. So basically we have the fragment UVs here. So if we just feed in, if you create a UV curve without the abs, so it's just sine seconds, what we can do is basically anim UV equals r.add fuv, and then we add the UV curve to it. So this is going to go between -1 and 1, and it's going to animate the UVs. So instead of the fragment UVs, we can pass in the animated UVs. And now if you go back to Spark, you see basically it's going to animate between these two values, smooth function in the smooth fashion. And what we can do is actually just multiply this by something like 0.1 so that it doesn't go too much. Now it's just oscillating halfway, and the blue is a bit too dark for my taste, so I'm just gonna do add here. So there you go. We basically used the smoothstep function to create this mask between the scene and animated the UVs to move the mask around. And we can even just output the UV color again. So now you see it's basically this animated mask over here. So let's go back. So just one more thing. We've done a bunch of computations of curves as well. So I just wanted to point out that, so all this basically is not dependent on the UV coordinates or the colors or positions of the pixels. So it's basically something Spark can run on the CPU. So this stuff, it's going to actually go here, and CPU code is going to do this, because the time value is, it's the milliseconds elapsed since the first frame. So that's something the CPU is computing. Then the sine wave and the absolute, that's also, again, it's based on a CPU value. So the input is a CPU value, so it's going to do these on the CPU as well. So it's basically going to compute all these values on the CPU and send them to the vertex and pixel shaders. So anything which is computed on the CPU side, and if one of the shader units wants it, it's just passed directly. So that stuff doesn't go through the interpolators. So let's just go through this again. So basically we have all the CPU code, then the UVs are calculated on the vertex shader. Then we send that to the fragment stage. After that, we compute the colors, which is in the fragment stage. Then we can basically add the color to the curve value, which was passed in from the CPU. Then we do the same here, and then we add the curve value to the UVs as well, which is again the same value which was passed in is now used to modify the UVs. Then we do the step functions in fragment space in the fragment shader as well. Then we do the linear interpolation. We use it to compute a blended color again on the fragment shader. So, and then we use that to generate the final output. So basically, yeah, all this code is in the fragment shader. All this code is going to be on the vertex shader, which is literally just computing the UVs and passing them along. And then this is on the CPU. Okay, so that's it for now. Hopefully you have a better idea of how shaders work and where the different parts of your code are going to run in Spark and how you can move stuff from one place to the other. Okay, so in the next episode, we'll continue a bit more in the shaders, and I'll show you how sampling works and how you can do blur functions in shaders using loops, which makes it much more easier to create as compared to patches. And that's one of the areas where scripting really shines in Spark. So I'll walk you through that side of things. Alright, so I hope you found this video useful. Let me know if there's any questions in the comments below, and I'll explain it in a bit more detail. Don't forget to like and subscribe if you found this video useful, and I'll see you guys next time.